Hello everyone, I am Disha Bharadwaj, currently pursuing computer science engineering from Sri Venkateswara College of Engineering. And today we'll be talking about a research paper on DyCache, a dynamic multi-grain cache management for irregular memory accesses on GPU. So today we'll be going through the introduction, motivation, dynamic multi-grain cache management, architecture overview, details of the architecture, methodology, evaluation, related works and conclusion. So let's get started. The paper discusses the challenges of memory divergence in GPU architectures, particularly how irregular memory access patterns lead to inefficient utilization of the L1 cache. It introduces DyCache, a dynamic multi-grain cache management design that adapts cache granularity based on runtime memory access patterns to improve cache efficiency. The authors highlight that DyCache retains the benefits of wide cache lines for regular memory accesses while optimizing for irregular patterns, thus enhancing overall GPU throughput. Motivation: memory divergence and inefficient utilization of L1 cache. Memory divergence occurs when the LDST unit generates multiple memory requests due to non-continuous data access, leading to inefficiencies in the L1 cache. The paper emphasizes that the mismatch between fine-grained data demands and coarse-grained cache lines result in increased cache miss rates and wasted bandwidth. Prior studies indicate that the average cache efficiency is only 58%, underscoring the need for improved cache management strategies. Fine-grained cache management. Fine-grained cache management techniques such as sector cache and elastic cache aim to enhance cache efficiency by allowing smaller data chunks to be stored within cache lines. These methods provide mechanisms to manage cache at a finer granularity, but often lack the flexibility needed for varying memory access patterns. DyCache builds on these concepts by enabling dynamic adjustments to cache granularity, thus addressing the limitations of static fine-grained management. Problems of static fine-grained cache management. Static fine-grained cache management requires users to pre-configure cache settings, which can be inefficient due to varying memory access patterns during application execution. The paper illustrates that applications may experience different access patterns across phases, necessitating a more adaptable cache management approach. DyCache aims to overcome these limitations by automatically adjusting cache granularity based on real-time profiling of memory access patterns. Dynamic multi-grain cache management. DyCache is introduced as a solution to improve L1 cache efficiency by dynamically switching between fine-grain and coarse-grain cache management based on memory access patterns. The architecture of DyCache includes a multi-grain management unit that profiles memory accesses and selects the appropriate cache granularity. This dynamic approach allows for better handling of memory divergence, reducing the burden on off-chip memory and enhancing throughput. Now let's look at the architecture overview. The architecture of DyCache includes a tag match controller that manages cache hits and misses by utilizing both common tags and chunk tags. The LDST unit coalesces memory requests to optimize data fetching while profiling unit record access patterns to inform granularity selection. DyCache design allows for efficient memory access by adapting to the specific needs of the application at runtime. Tag match. A memory access is considered a hit when both the common tag and chunk tags match the corresponding entries in the cache. The DyCache architecture processes memory accesses by comparing tags and managing cache coherence effectively. This tag matching mechanism is crucial for maintaining high cache efficiency and minimizing access latencies. Cache granularity selection. DyCache employs a sampling method to evaluate memory access patterns and determine the optimal cache granularity for subsequent operations. The selection process considers both cache miss rates and the ratio of fine-grained accesses to ensure efficient cache management. By categorizing memory access patterns, DyCache can dynamically adjust its granularity to optimize performance. Supported cache granularity. DyCache supports multiple cache granularities including 32 bytes, 64 bytes and 128 bytes, allowing it to adapt to the needs of emerging GPU applications. The flexibility in granularity is essential for addressing the diverse memory access patterns present in modern applications. This adaptability positions DyCache as a forward-looking solution for future GPU architectures. Methodology. The research utilizes GPGPU Sim 3.2.2 for simulation, employing a GTX 480 configuration to evaluate DyCache's performance against existing cache management strategies. The methodology includes comparative analysis with elastic cache to highlight the advantages of dynamic multigrain management. The experimental setup is designed to rigorously assess the impact of DyCache on cache efficiency and overall GPU throughput. Let's look into the evaluation now. Performance. DyCache demonstrates significant performance improvements, achieving a 40% increase in IPC for applications with irregular memory accesses compared to the traditional cache management. The evaluation reveals that DyCache does not negatively impact the performance of applications with regular memory access patterns. The results indicate that the optimal thresholds for cache management granularity are crucial for maximizing performance across diverse applications. Sensitivity study. Cache volume. Increasing cache volume leads to a drop in the speedup of DyCache against baseline caches, highlighting the importance of efficient cache management. The study suggests that as datasets grow, the need for effective cache strategies becomes even more crucial. DyCache remains relevant as applications demand higher efficiency in cache utilization. Sampling period length. The length of the sampling period affects DyCache's ability to adapt to changing memory access patterns, with longer periods benefiting applications with fluctuating patterns. An adjustable sampling period allows DyCache to quickly characterize memory access patterns while minimizing unnecessary granularity changes. This flexibility enhances DyCache's responsiveness to dynamic workloads. Related works. Memory access coalescing. The paper discusses existing memory access coalescing techniques that aims to optimize memory requests in GPU architectures. DyCache complements these techniques by providing a multi-grain cache management approach that enhances L1 cache efficiency. The integration of both strategies can lead to a more effective memory system for GPU. Fine-grain cache management. DyCache's dynamic management contrasts with static fine-grain cache management approaches, offering adaptability based on runtime conditions. The paper combines DyCache with elastic cache, emphasizing its ability to adjust granularity in response to memory access patterns. This adaptability is crucial for optimizing performance in diverse application scenarios. So, in conclusion, DyCache effectively splits cache lines into varying sizes based on memory access patterns, improving cache efficiency for irregular accesses. The dynamic selection of cache granularity allows DyCache to maintain high performance for both regular and irregular memory access patterns. Experimental results validate DyCache's capability to enhance GPU throughput significantly while preserving the performance of traditional applications. So now we reach the end of the video. Thank you very much for watching and please consider liking it.